Hi, this is Tom, and in this video, we're going to take a look and find out the law of the law of addition for probability, law of addition, law of addition for probability, when events are not mutually exclusive. Okay, now let's look. I copied and pasted up here at the top the data set from our last example. These were students that we had interviewed and asked what kind of transportation they'd used to come to school one day. Well, what if I told you that I know more about that data than I first revealed? And here's what I know. I know the gender of those people. So I'm going to recreate my table. And here's how it's going to be. So now we're still going to have our car people, truck drivers, SUV or minivan people, the one folk that took the bus, and we'll put a total here. But now we know one more thing about these people. We know their gender. They're either male or they're female. Okay, now the males, let's see, 13 of the males drove a car and 25 of the females drove a car. 13 males, 25 females, and notice that's still 38 people that drove the cars. And so we'll have our total here at the bottom, on the bottom row as well. So for the people that drove a truck, we had one of the folks was a male and 2 were females. So there's still 3 people driving a truck. And then for the SUVs or minivans, 5 of them were males, 3 of them were females, for a total of 8 still. And the person that took the bus was a male. And now though, what do we have? So notice this bottom row totals out like we would expect it. And we already know that it adds to 50. So let's check our table going the other way. How many males do we have? Well, we have 13. We're going to put a little, maybe a little orange plus sign, a little plus. Plus 1 more is 14, plus 5 more is 19, 1 more is 20. So we have 20 males. And let's do that again. For our females, we have 25 plus 2 is 27, plus 3 more for 30. So notice we know we made our table correctly because the total of 20 plus 30 equals 50, and then the total on the bottom row also gives me 50. So everything is correct. Now, if I asked you, let's ask a few questions. The first one is, remember we said that the categories of transportation were mutually exclusive, meaning you could only drive a car, or you could only drive a truck, or you could only drive an SUV, or you could only take the bus that day. And then the gender is also mutually exclusive. You're either a male or you're considered female. And so those are all mutually exclusive events. And we've already been through the probability of cars and trucks. We could let's find this though, the probability of being male. Well, that's going to be 20, because there's 20 males out of the 50 total. 20 out of the 50. And let's try again. For the females, the probability of a female, well, there's 30 females out of 50 total students. And we're not going to reduce those fractions yet. It's because it's easier to deal with a common denominator up front and then reduce, as opposed to getting a common denominator and then reducing again. So we're going to just leave those, but you should, if that was the end of our problem today, you'd write 2/5 for the males and you could write 3/5 for the females. Now, let's make this problem more interesting. Let's take a look at this. Let's ask this question. What is the probability of randomly selecting a person that is a female and drives a car? And she drives a car. Well, let's see. So this is a much tighter restriction because we can't just pick a female, because some of them drive trucks and some of them, sorry, I just messed that up. Because some of them drive trucks and some of them drive SUVs. So I can only want females that drive a car. So I'm restricted to this 25 down here. So there's the probability of randomly selecting a student that's female and drives a car is 25 out of the 50, 25 out of 50. Okay. Now, let's try this. Let's try, what is the probability of randomly selecting a student that's either female or she drives a car? Well, let's just start this problem. Let's start this problem exactly as we learned for an or statement. That means add. So that would be the probability of a female plus the probability of driving a car. So the probability of a female we found to be 30 out of 50. The probability she drives a car is 38. The person drives a car is 38 out of 50. Now, watch this. We have a problem. What is that problem? That problem is that 30 plus 38, that's 68 out of 50. Well, right off the bat, we know we have a problem because the probability can never be greater than 1. What happened? Did we do something wrong? And what we did is we just didn't look all the way into the problem. And I want to show you what we're missing. So I'm going to use this orange, and I'm going to just draw a line here. So when I looked at the females, that meant I looked at this entire row, all the way to those 30. When I looked at the people that drove a car, I looked at this column here. Notice those two lines intersect. And where do they intersect? They intersect at the females that drive a car, meaning female and a car. So we counted those females once in the females, and we counted them again in the cars. So they got double counted. When that happens, when events are not mutually exclusive, you have to subtract that probability that both things can happen. Female, I'm going to scoot this over a little bit. It's getting kind of tight there, so let me scoot all that over. Oops. Okay, so now what we want... Okay, now we can subtract the probability of the female and driving a car. We have to subtract the overlap that we counted twice. Well, we already found that. The probability of someone being female and driving a car is 25 out of 50. So now, our 68 out of 50, we subtract 25 from that. We subtract 25 out of 50 from that. And so, let's see, that's going to be 43. So the probability that someone is female or drives a car is 43 out of 50. And that is how you deal with the law of probability, the law of addition for probability when events are not mutually exclusive. Thanks for watching.